In this video, we want to introduce you to percent yield. Percent yield is used to calculate and compare how much a reaction produces compared to how much it should actually produce. So if we have a reaction where we put in a certain amount of reactant, we should be able to produce a certain amount of product. And what we do at the end then is figure out how efficient our reaction was, or how much of what we should have made we actually did make. This isn't too different from actually calculating, for example, your score on a test or a lab or a quiz, where you compare the points that you earned to the points that you could have possibly earned, with your hope being that you got 100% of the points. Well, we also hope that we made 100% yield and made exactly the amount that we should have in the lab. So, two quantities that we compare in order to do this, and then we'll talk about how we calculate percent yield. The first quantity is known as the expected or theoretical yield. This is the amount of product that you should be able to make based on the starting amount of reactant that you use. So if I put in this amount of each reactant, I should be able to make this amount of product. This is a calculated amount, and we use stoichiometry to do this. So expected yield is a value that you'll find through stoichiometry calculations, and it's kind of assuming that everything goes perfectly. If the reaction is perfect, nothing spills, nothing splatters out, I don't accidentally lose some of the product, it doesn't turn into a gas and escape. If I have everything that I expect in my flask or my filter paper or my test tube or whatever at the end, then my expected yield is that amount that I should be able to make if everything goes perfectly. Now, typically in the lab, not everything goes perfectly. So this is a calculated or theoretical amount that doesn't always work out. What we actually measure in the lab is known as the observed or experimental yield. The observed yield or the experimental yield is the amount that you actually make. And here we have the word "you" in quotes because sometimes this is a story problem where some theoretical scientist that's in the story problem carries out the experiment and makes this amount. So whether you do it in the lab and you actually measure this yourself, or if some Joe or Jane scientist does the measurement for you and you use their data, this is a measured amount that they collected in the lab and then measured a mass or a volume or something like that. In many labs that we do, we measure a finished mass at the end. That would be our observed yield. And again, the difference here is that the first is a calculated measurement, or the calculated value, and the second is a measured value. And then what we do is compare these two with the hope that they're the same. If they're the same, then probably everything went really well and you didn't lose track or spill or have anything that got lost during your lab, and you don't have anything extra, which can sometimes happen too. So calculating percent yield, here's the equation. Percent yield is calculated by taking the observed yield divided by the expected yield times 100. So the amount that you produced or measure divided by the amount that you should be able to have theoretically times 100. Again, this is calculated just like you take the points that you've scored on a test on the top divided by the expected or theoretical amount on the bottom times 100 to find your test percentage. So percent yield and the percent on the test are calculated basically the same way. Now, some examples of calculating percent yield. I'd like to go through a couple of examples here and have a couple that you can refer back to then that show a couple different ways that we would find and use percent yield in our calculations. So let's do that. If you don't have these problems already, then you can copy them down from the screen. Just put them into your notes. But if you picked up a copy of the page that has these problems, then you can just add and follow along right there on that sheet. This question says that for the equation shown below, if the reaction of 99.8 grams of oxygen produces 54.5 liters of carbon monoxide, what is the percent yield? So with these stoichiometry problems, contrary to kind of a typical stoichiometry problem, there are two amounts given here. And if there's only one number given in the problem, then we know exactly which one to start with. When there are two numbers given like this, it can be a little tougher to know. Do I start my stoichiometry with this 99.8 grams, or do I start my stoichiometry with 54.5 liters? And how do I choose? So here's the trick. When we're doing calculations of percent yield, generally we're going to find that the verb or the sentence itself sort of tells us how to set it up. This oxygen produces this carbon monoxide. And when we're finding percent yield, we're trying to figure out and compare how much we produce, how much we make. So this carbon monoxide is what's being made from the oxygen. If I start with 99.8 grams of oxygen, I should be able to make a certain amount of carbon monoxide. And I went in the lab and only made 54.5 liters. Generally speaking, when we do stoichiometry with these problems, we're going to be starting with a reactant, like oxygen in this example, and solving for the amount of product that can be made or yielded. So we're pretty much always going to find that the amount that you're given that is a reactant, for example here the oxygen, is going to be our starting amount. So let's start with 99.8 grams of oxygen. The question is asking how much carbon monoxide then should I be able to make, and then we'll find percent yield. Okay, so we need to balance this equation, of course, and we won't take a lot of time with the balancing here because by now you're all pretty good at balancing. This is 1, 3, 3, 3 when we balance this equation. So the first step in stoichiometry after we have a balanced equation is to get our amount converted into moles. Okay? Now, 1 mole of oxygen contains some mass of oxygen from the periodic table, and by now again you've done many of these sort of additions, so you can go to the periodic table and add this up yourself. Take the mass of oxygen times 2 and you'll have 32 grams. Remember, grams need to be on the bottom so that those units can kind of cancel out like so, and now we'd have moles. Our next step in stoichiometry is to multiply by a mole ratio, and we're trying to compare the oxygen, which is where we're starting in this problem, okay, to the carbon monoxide, which is what we're trying to figure out in this problem. And it turns out that these two substances are related by a 3 to 3 molar ratio. 3 moles of oxygen will give me 3 moles of carbon monoxide. So that's what we're going to put into our mole ratio step. 3 moles of oxygen will produce 3 moles of carbon monoxide. Now, oxygen again needs to be on the bottom so that it cancels out. This ratio of 3 to 3 would be true even if we flipped it upside down, but it wouldn't cancel out the units that we have in place already. So when we put the oxygen on the bottom in our mole-mole ratio, those moles cancel out and we're left with carbon monoxide. The last step of a stoichiometry problem is to get it converted into a unit that we can measure or actually handle in the lab. Usually, we don't typically stop on moles. Right now, if I punch this into my calculator, I would have some answer, and the units on that answer would be moles of carbon monoxide. We don't want to stop there. So, to get to the units that we actually want, we should look at the problem and make sure that we don't already know what units to use. What we're trying to do is get to an answer at the end of this that is our expected yield. Okay? This answer that we get over here will be, from stoichiometry, our expected yield. And we're going to compare that to our observed yield. This question says that we observed 54.5 liters of carbon monoxide. Now what I'm getting at is that this tells me the units that I want, liters of carbon monoxide, so that at the end we can compare apples to apples. So this last step should be converting us over to match these units of liters. And we know that 1 mole of carbon monoxide, as with any other gas at standard conditions, has 22.4 liters for a volume. So 1 mole of any gas, including carbon monoxide, is 22.4 liters. And finally, those moles will cancel out, and I'll be left with some units here, liters of carbon monoxide. Now, again, I'm assuming you guys can all punch these into your calculator and get a pretty good answer. So we won't take a lot of time to have you do that. You can punch it in and see if you can't get this answer too. If you want to pause us and do that, you can. But hopefully once you punch it into your calculator, you'll get an answer of right around 70, about 69.9 liters of carbon monoxide. Now, this is how much we should be able to make, the expected yield found by stoichiometry. In other words, if everything goes perfectly, that's how much carbon monoxide I should have. But the story problem here, the question says you actually produced, okay, this reaction produces only 54.5 liters of carbon monoxide. You made less than you should have, and that often happens in labs. Sometimes we make more, sometimes we make less, and our job is at least partially to figure out why. What could we do to make it perfect? But right now we want to figure out what our yield is. So to find percent yield, you can go back to that equation that you copied down a moment ago. Percent yield is our observed yield over our expected yield, and then take the whole thing times 100. So from our problem here, the observed yield given in the problem is 54.5 liters. Typically you'll find your observed yield is right there in the problem, or perhaps it's in a data table if you're given a data table with your question. And the expected yield we just found here from our previous calculation is 69.9 liters of carbon monoxide. Those units should match up because they're about to cancel out. When we divide, the liters of carbon monoxide will cancel out. And in the end, take that times 100 to get a percentage. You should find this is about a 78% yield. Now, as far as labeling this, you want to be sure to have percentage on there. And it's nice to have yield in there, at least in our minds, but it's good to put it on paper too, because there are other percentages that we can calculate for a reaction, like percent error, for example. And percent yield is the one we're looking at here. So this is like scoring a 78% on a quiz or a lab or a test. You might not be real happy with that on a test score, but in lab, a lot of times 78% is a pretty good score, because a lot of times reactions are just really hard to be 100% efficient on. Okay. Now, I'll make another video here on question number 2 on the same page, and we'll pause it. I'll end this video here, and you can pick it up with that one in the very next link. We'll see you there.